Hi, in today's video, we will take a look at another high voltage power supply. If you have been following my channel, you would know that I did a teardown and attempted repair of a Bertan 205A-05R 5 kV power supply a while ago. And unfortunately, that power supply had a bad capacitor inside a potted high voltage module, and I was not able to repair it. Anyway, long story short, I just got another Bertan power supply, and this one is also in the 200th series. This particular one is a 225-20R, which could output up to 20,000 volts with a 1 milliamp maximum current output. And because it is controlled digitally, I expect to see a bit more circuitry inside. Now, before I get started, I would like to stress that this is a high voltage power supply and we are dealing with potentially lethal voltage here. For someone who is not familiar with high voltage circuitry, I would highly recommend that you do not attempt to disassemble or play with this kind of equipment. Now, that said, for this one, it is relatively safe as the output current is limited to just above 1 milliamp. So even though the voltage could be very high, the actual current delivered would be relatively low. So you could, in theory, get a very nasty zap or shock if you accidentally touch the output, but it would probably not kill you. Anyway, you've been warned. I'm not quite sure about the vintage of this particular unit, but when we open it up later, we will see from the date codes at when this particular unit was built. Now, that said, these kind of high voltage power supplies have a relatively long shelf life, and this particular unit, I believe, are still being sold new at Spellman high voltage. So in theory, you can still buy the same unit that I'm showing you here from the supplier. So let's take a look at some of the specifications of this unit. And here I have the printouts for this series. And if you take a look, that the voltage regulation is less than 0.001%, which is quite good. It's only about 10 ppm. And the load regulation is also very good. It's roughly 50 ppm of the full load. And we can take a look at other aspects of this unit. If you take a look at the line I highlighted here, you will see that the current resolution for this 0 to 1 milliamp output is at 0.1 microamp, and the voltage resolution is 1 volt. So what does this tell you is that I'm thinking that it has at least a 15-bit DAC inside, because to have more than 20,000 intervals, you will need at least a 15-bit DAC. So we will see later what kind of a DAC or an ADC it uses inside. Anyway, so that's the specifications, and now let's take a look at the unit itself. Before we proceed to opening up this power supply, let's briefly take a look at the operating principles of this high voltage power supply. Like most high voltage power supplies, a lower voltage is stepped up using some sort of DC to DC converter, and then the voltage is regulated. So let's take a look at Spellman's application note. So here we have a basic diagram, not necessarily the diagram for this particular unit, but you get the general idea. So basically you have a DC to DC converter, and the control voltage is sensed on the high voltage side via some sort of either a high voltage divider or some kind of opto isolator. In order to achieve stable high voltage output, you really need a very stable voltage reference, which we will take a look when we open up the unit. And there also will be some kind of precision DAC and ADC to measure the high voltage. Anyway, so let's take a look. Before I open it up, let me just turn it around so you can see what is behind. So in the front, on the front panel, you have this rotary encoder to adjust the voltage and current settings, and you have a dedicated high voltage on-off switch, which is very important. Now let's take a look at the back here. So towards the back, you can see that compared to the 05A last time we saw, you can see that we have a set more transistors here. And this one does support GPIB, but we're not going to investigate that today. And behind here, you can also see that we have a program control. You can kind of control it remotely or locally, and right now both of these are set to local. And when the unit first came, it was marked as unknown condition, and I think I turned it on and couldn't adjust the voltage. I thought I got another bad one, but I went to read the manual and figure out that actually it was configured to be remotely controlled. So after adjusting that, everything seemed to be working. So I guess I was lucked out. Anyway, this one has the output is, I'm not sure what the standard this output is, but I actually don't have a mating output cable that can plug in. So I probably have to devise something later myself and to hook up to this. Anyway, so that's the back end of this unit, and let me take my screwdriver and open it up, and we'll see what's inside. Okay, so now with all the screws removed, we can open it up. Now the top cover just got removed. And let me take the camera off the stand and we'll take a look. So as you can see that the inside of this unit is significantly more complex than what we had in that 205-05R analog high voltage supply that we did tear down with last time. So let's take a closer look at what we can find here. On this main board, the only thing I can see are these op amps. So there's a LF412, which is a, I believe, a JFET input op amp. And here we have some standard TL082s. And what is this one? So here is actually our voltage reference. This is a 8586 high precision 5 volt reference. So that's used for the unit, both for measuring the high voltage readouts and to generate the stable output current and voltage. And here we have more op amps. So that's pretty much all we have on this main board, all the op amps and voltage reference. And here is our some 317 and 33, well, not 317, but 7805 and 7815, 7915. So those are our power supplies. And then we have these okay, let's move to the right hand side a little bit. So what we have here is our potted high voltage DC-DC converter portion. And the output, as you can see, this two high voltage wire here, and connects to this block where you can interchange. You can unscrew these and place it the other way around. So the output would be, instead of a positive output, it would be a negative output. Okay, so now let's take a look at the front two panels. I don't think I'm going to take this apart because the front board here, this is just for display and input, and there's some chips there, here and there, handling the display. and the multiplexing of the input buttons, and perhaps handling the rotary encoder. Actually, no, I take it back. The rotary encoder is actually, if you can see here, it's actually outputted to the second board here. So I think the front board here is just for the display and the buttons. Now, this board is probably the most interesting one, so we will take a closer look. I'm still trying to find out where the ADC is located, and I so far haven't seen it yet, but let's take a closer look here. So down there we have, again, some more op amps, and this one is I think it's AD 712. Which I believe is also a high-speed dual op amp. And oh, okay. So I spotted the ADC here, and let me just let it take a moment to focus. And let's see if we can. So that chip there, marked as ICL 8068. That's actually a 14-bit and 16-bit, 14 to 16-bit A to D converter. So if you recall, I mentioned earlier that this unit, from its specification, we can see that it at least used 15 bits because to achieve that 0.1 microamp output adjustment and 1 volt resolution adjustment. So that's where the magic happens. And other than that, I think we just have some, and this ICL 7104 is just a 4.5 digit A to D converter, and possibly for the display. And then we have some RAM here, and let me see this one. And you can't see it on the screen here, but that's a CDM 6116 AE2. That's a 2K by 8 bit RAM. And we have here, the chip tucked in here is an Intel 8085. So they're actually using an Intel processor to control this whole unit. And then we have some EEPROMs that are, basically the sort of firmware. So that's pretty much all she wrote. And because this unit also has GPIB capability, so I think that one of the chips here must be handling GPIB, either this one or the one down here, which is, I can't really see, but it has to, because that's where this cable is coming in at. And here we can set the different addresses of the GPIB. So that's pretty much all she wrote inside. And let me put it back so we can do a couple of experiments. And as I mentioned before, this high voltage power supply uses a special high voltage output connector, and I actually don't know the name of what this connector is. Maybe if you are familiar with the high voltage connector types, you can post a comment below, so we will know what this connector is. But anyway, so this one is actually a threaded, has a threaded grounded casing, and with a rubber guard in the center, and also around the inner connector. So the diameter of this is around 1 inch. So for that, I actually had to make a connector myself. Actually, it's not that difficult. So here you go. Here's the connector that I made. Basically, I use a cap from a this aerosol gel, and then I happen to have this plastic ring, and we thread inside. And then I use a little piece of I think it's a tube, plastic tube from something, that so that it would mate. You would actually go over the inner this rubber section, and then I have a piece of a copper wire that sticks out that would actually go into the connector itself. So let me actually show you this a little closer so we can see exactly how that works. So let me just prop this up. Okay, so you can see here, if I plug this in, so the middle connector goes into the hole right in the middle, and the tube here covers this inner section, and the outer section covers the tube. So here is how it goes, and then we can screw this on. Okay, so that's how this high voltage connector works. But actually, this one works quite well. Unfortunately, I only have a small section of this. I think it's 40 kilovolts rated cable. So unfortunately, this is going to be a little short for the experiments, but it's actually still useful rather. One thing is that I don't have a appropriate high voltage alligator clip. So this kind of an alligator clip, as you will see later, is that it has some very sharp edges. So above certain voltages, you will see a pretty significant corona discharge through these kind of sharp points. So you'll hear some kind of hissing and discharge glow around this alligator clip. But other than that, it's definitely useful. So now let's first measure the output voltage to see how accurate it is. For that, I'm using this high voltage. Oops, sorry about that. I'm using this high voltage meter here. Actually, this probe was broken, so I had to make the high voltage resistor myself and put it inside again. So this one is a little bit off, but we're just going to see, whether or not this thing is operational. Let me power on the unit. As the processor initializes, it does take a little bit of time to initialize, and right now it shows the model number 225 and -20. And now the high voltage output, this is the voltage measured. So it's normal for this kind of a high voltage power supply to have some residual voltage when it's not when it's set down to 0. So let's turn on the high voltage, and this unit has a couple of ways to adjust the output. So I'm not going to bore you here. I'm just gonna adjust the output directly. So I'm going to say change it to voltage. Okay, so let me turn on the meter here. So right now we're setting to 1, we're divided by 1,000, so roughly 1,000, okay? So let's increase the voltage here. So we're at roughly 200 volts, and here you see a 0.20, so that's that basically is a 200 volts. Let's increase to 1,000. So far so good. And I actually kind of really like this rotary encoder because it's really smooth, and depends on how fast you are rotating it. So it's a velocity sensed. So the faster you rotate, the faster the output changes. But right now we're just going to change gradually. So now it's 1,000 volts. So it's give or take. Again, as I mentioned, that the high voltage probe I rebuilt might have some errors because of the resistors I used were not very high precision. Okay, so now let's see, 1,500. So it's still pretty much tracking. So we'll just kind of keep to let it run its course. So let me do it faster now. So now it's 50, 60, 70, 80, 90, and now it's So a little bit off right now, you can see, but I don't know if it's because of this meter, the meter I'm using, or it's the unit. So as far as we're concerned, it doesn't really matter that much. So let's adjust it all the way up. So now we're at 20,000 volts. Okay, I can hear a discharge somewhere. It's probably, oh yeah, it's from the tip that I was holding that meter. So, and it looks pretty good. Okay, so now let me unhook this probe. By the way, if I turn it off right now, you can see that the high voltage doesn't drop immediately, but it's, you know, dropping pretty fast. So as long as you don't touch it immediately after, you should be fine. Okay, so now let's do a couple of experiments. So let's take a look at a very classic experiment. And this experiment, you probably have seen it elsewhere, but I do want to clarify a couple of things. So here I have two metal plates, and these are just PCBs that I mounted onto this right angle brackets so they can stand up. And one side would be connected to ground, the other side would be connected to this high voltage. Now what you will see is an object inside would be oscillating back and forth, because once it touches the positive side, it would be charged up, and when the charge is the same as whatever the voltage, the potential of this plate is, the force gonna, you know, be canceled out. So it will swing back to the ground plate, and as soon as it touches the ground plate, it will lose all the charges. So then you will be attracted back to the other plate. So the cycle continues. Now, most of the people who do this experiment would use a metal piece of aluminum, or a, you know, like a, or some piece of a small metal objects inside. But I wanted to point out is you don't necessarily need a metal. Anything that can dissipate charges. So no matter how high the resistance is, it works equally well. So for that, I actually took this piece of rubber. I think it's from a printer toner, the printer roller rather. So it really has a very high resistance. So if you measure it, it's in a giga-ohm range, but it should work just as well. So let me hook this up and I'll show you. And for that, I'm going to, so right now I'm just going to check the power is off, so I don't want to shock myself. So let's set this up. We'll put this around this distance, looks good. Okay, so this distance looks just about right. And we will connect a high voltage to this end. So right now it's the high voltage is not on yet. And we'll connect the ground to this plate right here. Okay, so now I'm going to turn on high voltage. And once I turn it on, you will hear a little bit of hissing noise, as I mentioned earlier. That's just because of the connector has sharp edges. So there's nothing to worry about. So now I turn on high voltage. I'm going to ramp it up. Actually, I'm just going to set it all the way up to 20,000. So now it's sitting at 20,000 volts. And the reason I have to do it sideways is because I don't have, the cable is not long enough. So anyway, so now I'm just using the string to gradually lower this object to between the fields, and watch what happens. So basically, this is exactly what I mentioned before, and so this piece of rubber would be bouncing back and forth because of the charge that between, you know, charge and discharge, depending on which plate it touches. So now, this is really fun, and you can do this, you know, like with, surprisingly, you can do this with a lot of heavier objects as well, depending on the field strength. So, and let's see if we can make it lower voltage and still make it work. So now let's turn it down to 10,000 volts. By the way, you probably can't see this, but I'm just adjusting. Oh, so now it's roughly, okay, give or take 11,000, 10,000. Okay, 9,000. Oh, it's a little bit touchy here. So, good enough. 10,000. So let's move it slightly closer. By the way, this is ground plate, so I can touch it by my hand. So let's put it slightly closer to see if we can still do that with this heavier object. Yeah, as you can see, we can still do that. It's a little, the action is a little bit weak, but nevertheless, it's still you can still bounce back and forth. So yeah, that's quite nice. So I suspect we can still keep it, move it even lower. So let's now go to 5,000 volts. Hang on. 6,000 volts. All right, so 500. Yeah, 5,500. That's close enough. Let's see if we can do this. So it's certainly pretty weak now, the action. But if you were using a lighter material, I suspect that will work pretty well. So let me just move it closer. As you can see, it definitely still works. It's still oscillating inside. If you just yep. Anyway, so that's the first experiment, and let's move on to our next experiment. So one of the experiments I'm going to show you is to do a non-contact voltage measurement using a field meter. And for that, I'm going to set up a some insulated block up here so that we don't discharge against the metal casing, which is ground level. And let me up here. And what I'm going to do is I'm going to hook the output from the high voltage to the terminal here. Okay. And this doesn't want to stand still. That's okay. All right, so that's good enough. So now what I'm going to do is I'm going to take this field meter. You've seen this before, and I did a teardown and analysis of this meter. So let's first turn it on and pointing to a ground reference, and I'm going to null the output. So that's pretty good right now. So right now we're reading about 0.08. Okay, so now actually let's just zero it out. Okay, so now this is roughly zeroed. And now what I'm going to do is I'm going to turn on the high voltage and set it to 10,000 volts. So this time we're going to use a set functionality. So we set, when you are setting the voltage, it actually doesn't really output that voltage yet. So basically we can precisely set to what we want to get. So this time is 10,000 because that's the maximum this unit is capable of. It's more of a discharging hazard than actually what this is capable of, because as the voltage goes higher, the distance required to discharge becomes larger. So this thing, you have to put that 1 inch in front of the object to try to measure. So in order to eliminate the discharging hazard, it is limited to 10,000 volts. Okay, so let's set it to 10,000. It doesn't need to be that accurate. Okay, 10,000. Now as soon as we hit enter, that plate will be energized. Okay, so now we hit enter. So let me just put this here. Okay, so now enter. And you can see already we are picking up some readings. But as I move this closer, I'm going to try to let you still see the reading here. I'm going to do a hold on that. So this is roughly 1 inch. Okay. So now I'm going to do a hold. And as you can see that we are reading 10.71 kilovolts. Now that's probably because the distance is not that precise, but nevertheless, we just showed that we can use a field meter to read the whole high voltage output. So now, which brings us to our next experiment. Last time I explained how this field strength meter, how it works. It works by having basically a ground cage, and behind it we have a little metal plate. We measure the induced charge on this formed capacitor, and to deduce the actual field strength. So for that, I actually built a proof of concept sensor to show you exactly how that works. So for that, I have a piece of aluminum cable. I have a piece of aluminum, and I bend it in like so that I can stand it up. So by the way, I just turned that off, so let me move that out of the way. We'll do that later. And at the back, I stuck on a piece of PCB, and as you can see, this is a single-sided PCB. It's facing backwards, so this metal film and the aluminum forms a capacitor. Okay, so I have a hole here. So basically, the idea is when this is placed into a field, the field and with the aluminum case grounded, this would induce a voltage on the capacitor here. So by measuring the capacitor, by measuring the voltage induced here, we can determine how what the voltage applied in the field is. So that's the same idea as what I just showed you from this field meter. So anyway, so here's the setup. So on to the left here, I have the high voltage applied to this plate, and to the left here, I applied basically I connected this metal to this piece of aluminum to the ground. So this is a ground lead, and connect right here onto the case. And then here's my electrometer, and let me zoom in here. So basically the electrometer ground is connected to the aluminum as well. And the electrometer's positive is connected to this red wire, which connects to the other side of that, which I showed you earlier, the other side of that PCB. So basically it's measuring the capacitor output voltage. So now this is a very sensitive setup, so I'm just going to ground it right here. So actually let me put this up here so that it doesn't oscillate so much. Okay. So what is going on is I wanted you to concentrate on the electrometer to see the relative voltage movement. Okay. So if I turn up the voltage, you will see that it's going up. Okay. Now if I turn it back down, you will see that this voltage drop. So this experiment is a little bit difficult because we have some static charge on this plate. However, you can definitely see if I turn this, if I dial up the voltage, you can definitely see that it is the induced voltage is going up, and if I dial down the voltage right now, you'll see that the induced voltage is going down. So this is generally the principle of how that field strength meter works. Now, of course, as I explained before, to make that really useful, you have to have some kind of a chopper stabilized amplifier, so that at each interval of the measurement, you know that you are starting from a known zero, so that you can calibrate against what the theoretical value is. Whereas right now, this particular setup, you see the value drifts quite a bit because of the nature of this very high resistance input of the electrometer and our very small sensing element here. Yes, I know what you're thinking. We can't do a high voltage supply testing review video without seeing some sparks, and that is something I really don't want to do. But you know, and this is a relatively safe current level, as I mentioned before. So right now we turned off the current limiting, so you will see the discharge if I move this earth referenced alligator clip to this surface. Here we go. Here you'll hear some hissing. There you go. Anyway, so I hope you have enjoyed the video and learned something new. And if you did enjoy the video, please give it a big thumbs up and remember to subscribe. I will catch up with you next time.